Ever feel like you need a secret decoder ring just to understand all the latest buzz around artificial intelligence?
Yeah,
Maybe you're, skimming articles before a big meeting, wishing you could just grab the key stuff without getting totally lost in jargon.
definitely happened.
You're not alone. Welcome to the Deep Dive, your shortcut to becoming, well, seriously well-informed. We're kind of like your expert guides, wading through all that information overload to bring back the essentials.
And the way we do that is by taking a really close look at the source material you, our listener, share with us. We pull out those crucial nuggets, the core knowledge, the understanding that really matters, or aim, give you a solid grasp of complex topics, but without making you feel overwhelmed.
Exactly. And today, we're focusing on a listener we call the learner, someone who's keen to get a solid handle on artificial intelligence quickly and effectively. You sent us excerpts from an academic course ia.pdf, and wow, it covers a ton of ground.
It really does.
We're talking about how AI is defined, its history, all the different areas within AI, where things stand today, and even diving into how AI solves problems using things like search algorithms, planning, playing games, representing knowledge.
And that intro to machine learning, looking at decision trees specifically.
Right. It's a huge subject, but our mission today is clear. Extract the most crucial, the most interesting insights to give you a real foundation in AI. So, okay, let's unpack this. Defining AI. Where do we even start?
Well, you might think there's a nice simple definition everyone agrees on when we talk about artificial intelligence.
Yeah.
But what's really fascinating here is that even the experts have wrestled with this.
Really?
Yeah, the author of our source material even mentioned how tricky it was writing that first chapter, because there's just no single universally accepted definition, which really tells you something, right, about how dynamic and, well, still evolving the field is.
It's not like defining gravity, then, it seems. We've got a whole bunch of attempts at defining AI in our source material here. Like, back in '85, Charniak and McDermott saw it as the study of mental faculties using computational models.
Okay, so focused on the mind, computationally.
Then, '98, Poole and colleagues focused more on designing intelligent agents, agents that do things.
Right. And Rich and Knight in '90 took a more, maybe practical angle, making computers do tasks humans are currently better at.
Okay, I see the differences already.
You can definitely see different ways of thinking there. In '78, Bellman talked about AI as the automation of reasoning activities. Things like decision-making, problem-solving, learning.
So automating thought processes.
Pretty much. Winston in '92 broadened it to the study of mechanisms enabling agents to perceive, reason, and act. So adding perception and action.
Perception, reason, action. Got it.
And Nilsson in '98 gave a very general definition. The study of entities with intelligent behavior. Very broad.
That is quite a range. And it's interesting seeing the definitions the students in this course came up with, too. They talked about machines reasoning on their own, adapting, building machines that are kind of like humans in how they see or understand, and creating software for tasks, needing high-level mental stuff like memory, even feelings, though. Wow, that last one is definitely a huge debate in AI.
Oh, absolutely.
Yeah.
And one student defined intelligence pretty simply as the ability to understand things, and AI as if the software learns on its own. Another saw AI as a set of techniques aiming to approximate human reasoning. These student views really capture both the, big ambitions and the ongoing debates.
Okay, so looking at all these different ideas,
Yeah.
what are the real core differences in how people are thinking about AI? Where do they diverge?
Well, if we kind of step back and look at the bigger picture, you see two main ways these definitions tend to differ. First, some focus on the observable behavior, what the AI can actually do.
Right.
Others are more interested in the internal workings, how it reasons. And second, some definitions compare AI directly to human intelligence, while others use a more general idea of rationality or achieving goals effectively, which isn't necessarily tied to how humans happen to do things.
That makes a lot of sense. So the source then kind of breaks it down into four main ways of looking at AI based on those distinctions, right? Let's dive into those.
Exactly. The first one is about creating systems that behave like humans. This idea is really strongly linked to Alan Turing and his famous Turing test.
Yes, the Turing test.
The basic idea, you probably know, is if a machine can chat so convincingly that a human judge can't tell if they're talking to a machine or another person, well then we should consider it intelligent. It's all about that outward performance.
Performance is key.
And as the source mentions, people have suggested more complex versions of the test that would also assess things like perception or the ability to physically interact with the world.
Okay, then we've got the second view. Creating systems that think like humans. That sounds like a much deeper dive into our own minds.
It really is, yeah. Because this view sees AI almost as an experimental science. To know if a system thinks like a human, we first need to really figure out how humans think in the first place. It's not just about getting the same answer. It's about the AI using, hopefully, similar processes to a human brain.
Right, so mimicking the internal mechanisms, not just the results. What about the third way? Systems that think rationally.
Okay, here the focus shifts toward logic. The goal is to build AI that reasons perfectly, according to the strict rules of logic. But the source points out some real challenges here.
Like what?
Well, for example, things humans do easily, like seeing or understanding language, aren't always easy to capture perfectly in logical rules. Plus, the sheer amount of computation needed for totally logical reasoning in every situation is just way beyond what our current tech can handle.
So it's a very high, maybe impractical standard. And the final category, creating systems with rational behavior. How's that different from thinking rationally?
This is a bit broader. It's about creating agents that act in a way that best helps them achieve their objectives, their goals. Logical thinking can be one way to be rational, sure, but it's not the only way.
Okay.
Think about automatically pulling your hand away from a hot stove. That's a rational behavior, right? It protects you.
Yeah.
But it's not necessarily the result of some complex logical deduction. It's a reflex, but a rational one.
That's a great example, yeah. So even though we have these different philosophical viewpoints, does it actually change how AI research gets done day to day?
Well, what's interesting is that, according to the source, these different ideas about what AI is might not actually change that much about how most AI researchers work.
Huh.
Many are just driven by the fascinating problems the field throws up, Regardless of the ultimate definition of intelligence, it's often more about exploring what's possible than sticking rigidly to one particular philosophical camp.
Okay, that gives us a good handle on what AI is, or maybe what people think it is. Now, let's rewind a bit. Where did all this start? The source gives us a brief history, kicking off with a gestation period.
Yes, roughly 1943 to 1955. This is when we saw the initial work that really set the stage, even before the term artificial intelligence was common.
Right.
In 43, McCulloch and Pitts introduced their model of artificial neurons, a hugely influential early concept. Then, Hebb proposed a rule for how connections between neurons might change as we learn. That principle is still key in many learning algorithms today.
Burning rules, okay.
And Minsky and Edmonds actually built the first neural network. Though it's interesting, the source notes that later on, it was shown these very early networks had limitations. They couldn't even solve some pretty basic pattern recognition problems.
Limitations discovered later. And of course, we can't forget Turing's big paper during this time where he introduced the Turing test we just talked about.
Crucial contribution.
Okay, fast forward a bit. The source discusses the rise of expert systems. What were those all about?
So the period between roughly 69 and 79 saw these systems emerge. They were designed to tackle specific, complex problems by using knowledge directly from human experts. Dendrol, created in 69, is often seen as the first real expert system.
Dendrol, what did it do?
Its job was to figure out the molecular structure of a substance based on its chemical formula and the results of a test called mass spectrometry. What's fascinating is that Dendrol relied heavily on what they called heuristic rules.
Heuristics, like rules of thumb.
Exactly. Educated guesses, rules of thumb that human chemists had developed over years of experience. They basically encoded that expertise.
So taking human expertise, putting it in a program, and MyCIN was another big one, right?
Yes, MyCIN was developed to diagnose blood infections. They used around 450 of these expert rules and actually achieved diagnostic accuracy close to human experts and significantly better than young doctors just starting out.
Wow.
These early successes really show the practical potential of AI,
Definitely. Then the timeline jumps to AI in industry, from 1980 to the present. Sounds like this is when AI started making a real-world impact commercially.
Oh, absolutely. In the early 80s, DEC Digital Equipment Corporation started using an expert system to help configure their complex computer systems. And the source highlights this. It actually saved them tens of millions of dollars every year.
Tens of millions. That gets attention.
You bet. Those kinds of clear financial benefits led many major companies to take AI much more seriously. These started forming their own AI research teams. Governments in the US, Japan, the UK also significantly ramped up funding for AI research around this time.
Makes sense. And then we have the return of neural networks from 86 onwards. It's funny how ideas cycle in science, isn't it? What caused this comeback?
Well, the mid-80s saw 4 different research groups independently rediscover a learning technique called backpropagation.
Backpropagation.
Yeah, and what's interesting is this technique had actually been proposed way back in 1969, but for whatever reason it just didn't catch on then.
Huh. Why was it so important when it reappeared?
This rediscovery was crucial because it provided a really effective way for neural networks to learn very complex patterns from data. Since then, machine learning, which heavily uses neural networks, has just exploded. It's become a super active and successful area with applications in all sorts of real-world problems like finding useful patterns in huge amounts of data mining.
And that brings us to modern AI from 1987 to now. What's the defining feature of this modern era, according to the source?
The source really emphasizes a shift towards greater rigor, a more formal approach in the field. Instead of relying so much on, say, intuition, current research tends to be grounded in solid mathematical theories or extensive experimental study.
More science, less art, maybe.
Perhaps. And there's also a much stronger focus on applying AI to solve practical, real-world problems, moving beyond purely theoretical work.
It definitely sounds like the field has matured. Now, the source then breaks down AI into a whole bunch of subdomains. It's clear that creating a truly intelligent system is a massive challenge, which explains why people specialize, I guess.
Exactly. The sheer complexity of intelligence, whatever it is, has naturally led to AI splitting into numerous subdisciplines. Each one focuses on a specific piece of the puzzle.
So what are some of the key areas the source highlights?
Okay, first we have knowledge representation and automated reasoning. This is all about how to represent information, facts, rules, relationships in a way a computer can understand and use to draw conclusions, even if that info is incomplete or uncertain or maybe even contradictory.
Right, handling messy, real-world knowledge.
And this area, as the source points out, is closely related to those expert systems we just discussed.
Makes sense. What's next?
Then there's general problem solving. This focuses on creating algorithms that can tackle a wide range of problems, not just ones in a specific niche area. Think more adaptable problem solvers.
Okay.
Natural language processing, or NLP. That aims to let computers understand, translate, and generate human language, written or spoken. That's the tech behind, translation apps, chatbots, voice assistants.
Right, stuff we use every day now.
Following that, computer vision. This is about enabling computers to see, to interpret images and videos. Things like recognizing faces, reading license plates, understanding medical scans.
Okay.
The source mentions an early example called LVN, which actually drove a car across the U.S. Needed a bit of human help, mind you, for things like highway exits, but still.
Still impressive for back then.
And handwriting recognition programs have become incredibly accurate now, as the source notes.
That's pretty amazing. And then we get into the physical world with robotics.
Yep, robotics is about creating physical agents, robots that can actually interact with and act in the real world. The source even gives a link to the Honda Asimo robot website if you want to see some cutting-edge stuff.
Cool.
A key application mentioned is using robots in surgery. They can assist doctors with incredibly precise movements and even enable remote operations.
Wow. Finally, machine learning, which we touched on with neural networks.
Machine learning is really fundamental to modern AI. It's about designing programs that can learn and improve automatically, just based on the data they're exposed to, their experience. The source mentions its close ties to pattern recognition algorithms, which pop up in tons of different AI applications.
It's fascinating how all these different areas connect.
Absolutely. And the source also emphasizes the strong links AI has with other fields: philosophy, psychology, neuroscience, cognitive science, linguistics, even economics. It's a truly interdisciplinary field, drawing on lots of different kinds of knowledge.
Okay, so that gives us a good map of the different parts of AI. What about the current state of the art? What kind of impressive things can AI actually do today based on our source?
The source gives some really striking examples. In games, the big milestone mentioned is Deep Blue beating the world chess champion Garry Kasparov back in '97. It was a huge moment.
I remember that. Big news.
Today, computers are expert level at checkers, backgammon, bridge. Interestingly, the game of Go proved much tougher. For a long time, programs were only at an average amateur level, though that's changed dramatically recently, even if not covered in this specific source.
Right, Go was the next frontier. What about computer vision? We mentioned Alvin.
Yeah, Alvin driving is a great early example. The source also reminds us about handwriting recognition, less than 1% error rates now. It even gives a link to a demo website, which is pretty cool to see.
Definitely check that out. What about planning and scheduling? This sounds important.
Okay, here's where it gets really impressive, I think. The Force mentions a system that autonomously controlled a space shuttle for 2 whole days.
Seriously, the space shuttle.
Yep, without human intervention. It planned its actions, detected problems as they came up, adjusted its trajectory. That's a pretty high-stakes application.
Wow, that is a huge leap in autonomy. What about those expert systems from earlier? Still around?
Oh yeah, medical diagnostic programs today can achieve reliability comparable to human experts in many specialties. The source even shares an anecdote about a human expert who initially disagreed with an AI's diagnosis in a tricky case. But then, after the program explained its reasoning step by step, the expert realized the AI was right and they had missed something.
That's incredible. It shows the power of explaining the why. And AI is also big in logistics.
Yes, massively. The U.S. Army used an AI logistics planning program during the 1991 Gulf War. They coordinated vehicles, equipment, soldiers, solved problems in hours that used to take weeks.
Hours versus weeks.
And the estimated savings were so huge, they actually exceeded the total amount the Army had invested in AI research over the previous 30 years.
That is an unbelievable return on investment, and we can't forget robotics again.
Right, as we discussed, robots in surgery, assisting doctors, enabling remote surgery. So AI is moving beyond just software into tangible physical help.
It really sounds like AI is having a growing impact everywhere. Now, shifting gears a bit, the source then dives into the more technical side, starting with problem solving and search algorithms. This is where we see the methods behind these impressive results.
Exactly. To understand how AI solves problems, we first need a formal way to describe what a problem is in this context. The source breaks it down into 5 key parts.
5 parts, okay.
An initial state where you start. A set of possible actions, what you can do. A successor function, what happens when you take an action. A set of goals states what you want to achieve. And finally, a cost function, assigning a value or cost to each action.
So it's a very structured way of thinking about any problem, and this can be visualized like a map.
Precisely. You can think of it as a directed graph, a map of possibilities. Each reachable state is a node, a point on the map. The actions are the arcs, the paths connecting those points. Finding a solution is like finding a route from your start node to a goal node.
And the best solution.
That's the one with the minimum total cost along the path, the cheapest or shortest route.
To make this more concrete, the source gives a couple of classic examples. The 8 puzzle and the 8 queens puzzle. Let's start with the 8 puzzle, le taquin, as the source calls it. Sounds fun.
Yeah, the teaser. For those who haven't seen it, it's a 3x3 grid with 8 numbered tiles and 1 empty space. You slide the tiles around to get them into a specific order.
Okay, I know that one.
So formally, the states all the different arrangements of tiles and the blank space. The initial state is just the starting layout. The actions are sliding an adjacent tile into the blank spot. The goal test is checking if the tiles are in the desired final order. And the cost of each move is usually 1, so we're looking for the solution with the fewest moves.
Sounds simple, but I bet it gets tricky fast. The source says it's used a lot to test search methods, and gets way harder with bigger grids.
Absolutely. The 3x3 and 4x4 versions are solvable by today's algorithms, but the 5x5 is still really tough because the number of possible arrangements just explodes. For 3x3, it's about 181,000 states. For 4x4, jumps to around 1.3 billion. And for 5x5, it's like 10 to the power of 25, just astronomical. Really shows the challenge of searching.
Wow. Okay, what about the 8 queens puzzle? That sounds intriguing.
The goal here is to place 8 chess queens on a standard 8x8 chessboard so that no 2 queens can attack each other. Remember, in chess, a queen attacks horizontally, vertically, and diagonally.
All right, powerful piece.
The source even shows a picture of an almost solution that fails because 2 queens are on the same diagonal.
So how is this formalized? The state space is putting 0 to 8 queens on the board.
Initially, yeah. The initial state is an empty board, and action is adding a queen to any empty square. The successor function just gives you the new board setup. The goal test is, do we have 8 queens and are none attacking each other?
And the cost.
Cost isn't really the focus here. We just want a valid arrangement. But what's really clever, the source points out, is how we can massively shrink the search space by realizing we don't need to even bother generating arrangements where 2 queens are already attacking each other. That simple idea cuts the number of states to consider from something like 3 times 10 to the 14, down to just 2057.
That is a huge saving. So these 2 puzzles represent different kinds of AI problems.
Exactly. The 8 puzzle is a planning problem. The sequence of moves matters. The 8 queens is a constraint satisfaction problem. Only the final state matters, not how you got there.
And the source gives more examples, like planning a flight.
Yeah, route finding. States are your current airport and time. Initial state is your departure airport and desired time. Actions are flights. Successor function updates airport and time, considering layovers. Goal is reaching the destination. Cost could be travel time or ticket price.
And scheduling jobs.
Yep. States are partially filled schedules. Initial state is empty. Actions assign a course to a time rim slot. Goal is a complete, valid schedule. Cost might be constant, just find a solution.
Even games fit this framework.
Right. For multiplayer games, states include whose turn it is. Initial state is the start setup. Actions are legal moves. Successor function updates the state and player turn. Goal is a win. Cost depends, maybe fewest moves. For chess, states are board positions plus player turn. Actions are legal moves. Goal is checkmate, etc.
So once we have this formal description, how do we actually find the solution? That's where search algorithms come in.
Exactly. The source outlines a general structure most search algorithms follow. Start at the initial state. Keep a list of states to explore. Loop. If the list is empty, fail. Pick a state from the list. If it's a goal, success. Return the solution. If not, generate its successors, states reachable in one action, and add them to the list. The key difference between algorithms is how they choose which state to process next.
And how do we compare these methods? Judge which is better.
4 key criteria, according to the source. Time complexity. How long does it take? Space complexity. How much memory does it need? Completeness. Does it always find a solution if one exists? And optimality. Does it always find the best, lowest cost solution?
Got it. Time, space, completeness, optimality. The source then dives into uninformed search algorithms. What makes them uninformed?
They're uninformed because they don't have any extra problem-specific information to guide them, no hints about which states might be closer to a goal. They just explore systematically.
Okay, just exploring blind, essentially. The first one is breadth-first search, or parcours en largeur, wide search.
Yes. Breadth-first search, or BFS, explores level by level. It looks at the start state, then all states one step away, then all states 2 steps away, and so on. Explores all possibilities at depth 1 before moving to depth 2. Implementation-wise, it keeps a list, a queue really, and adds new nodes to the end.
Like ripples expanding outwards, what are its pros and cons?
BFS is great because it guarantees finding a solution with the fewest steps, if one exists. So it's optimal if all steps cost the same. It's also complete a solution, eventually, assuming finite options at each step. The big downside, memory. It can need a lot of memory if the solution is deep, because it has to store all the nodes at each level. Worst case, if successors per state and goal is at depth P, it might explore roughly soft to the power of TP states.
Oof, yeah, memory could be a killer. What about depth-first search, parcours en profondeur, deep search? Sounds different.
Totally different strategy. Depth-first search, DFS goes deep. It follows one path as far as possible until it hits a dead end or a goal. Then it backtracks to the last choice point and tries a different path. Implementation. It uses list, like a stack, and adds new nodes to the beginning.
Like diving down one specific path in a maze, hitting a wall, backing up, trying another. Characteristics.
But unlike BFS, DFS doesn't guarantee the shortest solution, and it's not even guaranteed to find one at all if there are infinite paths. It could get lost down a rabbit hole.
Not complete, potentially.
Yeah, right. But its big advantage is space complexity. It only needs to store the current path it's exploring, plus the immediate siblings, much less memory than BFS in many cases, roughly proportional to the depth times the branching factor, not exponential in depth.
So a trade-off. Potentially faster or finds a solution versus optimal complete but memory hungry. Now, iterative deepening search. Parcours en profondeur iterative. Sounds like a combo.
It is. It cleverly combines the best of both. Iterative deepening search, IDS, does a series of DFS searches, but with increasing depth limits. First, DFS limited to depth 1, then restart, DFS limited to depth 2, then depth 3, and so on until it finds the goal.
So it searches layer by layer like BFS, but uses the memory-efficient DFS for each layer's search. What are the results?
Amazingly, IDS is both complete and optimal when costs are uniform, just like BFS. And while it seems wasteful re-exploring the upper levels, the total work is usually not much more than BFS, because most nodes are at the bottom levels anyway. Crucially, it keeps the low memory footprint of DFS. This makes it the preferred uninformed search for many large problems where you don't know how deep the solution is.
That sounds really elegant. Now, all these can revisit the same state, right? Redundant states?
Yes, 2 main ways. First, you might go back and forth, like A to B, then B to A, usually easy to prevent by not adding the state you just came from. Second, you might reach the same state via 2 completely different paths.
Okay, that seems inefficient.
It can be. To avoid re-exploring from states you've already fully processed, you need to keep a visited list or set. For BFS, this doesn't add much memory overhead since it's already memory heavy. But for DFS and IDS, adding a full visited list can dramatically increase memory needs, kind of defeating their space advantage. Yeah, so there's a trade-off there too.
Right. Save time exploring versus save memory. Okay, moving on to heuristic search algorithms. What's the key difference here? They're informed.
Exactly. Heuristic search algorithms use extra information, a heuristic, which is basically an educated guess or estimate of how close a state is to the goal. It guides the search, pushing it in promising directions.
Like having a compass pointing roughly towards the exit, even if it wobbles a bit.
Perfect analogy. These algorithms use an evaluation function, usually called F, to rank the states to explore next. The state that looks most promising according to F gets processed first.
And the source highlights a search as a key example. How does A star work?
A uses a specific evaluation function, Fn plus HN. Here Gn is the actual cost to reach the current state N from the start, and HAN is the heuristic estimate of the cost remaining to get from N to a goal. So Fn is an estimate of the total cost of the best solution path that goes through state N.
So it balances costs already spent due with estimated future cost H. The source uses that route finding example, Era to Bucharest.
Yes, figure 10 walks through it. It shows A considering different cities. It calculates the F value for neighbors of Arad, Sibiu, Timisoara, Zerend, using the actual road distance from Arad G, plus a straight line distance heuristic to Bucharest H. It picks the city with the lowest F, Sibiu. Then it expands Sibiu, calculates F for its neighbors, adds them to the list, and again picks the lowest F value node from the entire list to expand next. It continues until it reaches Bucharest, always prioritizing the node that seems most likely to be on the cheapest path.
That sounds much smarter than just exploring layer by layer. Now, the source also talks about local search algorithms. These seem different again.
They are. For some problems, especially constraint satisfaction like the 8 queens, the path doesn't matter, only the final solution state. Local search algorithms exploit this. They start with a potential solution and just keep tweaking it to make it better, without tracking the path taken.
And greedy local search is the basic version.
Yes. It starts with some initial configuration, like queens placed randomly, and repeatedly makes a small change, like moving one queen, to get to a neighboring state that looks better according to some heuristic, for example, fewer attacking queens. It's like hill climbing, always take a step uphill.
Sounds simple. Strengths and weaknesses.
Big pluses. Very little memory needed, just the current state, and can be fast if it finds a good path. For 8 queens, it might find a solution in a few steps. The big problem: it gets stuck easily on local optima.
Like reaching the top of a small hill when the real mountain peak is elsewhere?
Exactly. If all neighboring moves make things worse, it stops, even if it's not the best overall solution. The source says it only succeeds about 13% of the time for 8 queens because it gets stuck.
Not very reliable then? Ways to improve it.
Oh yeah. One way is allowing sideways moves, moving to a neighbor with the same value, hoping to cross a plateau to find another upward slope. Limit these to avoid loops. That boosts success rates significantly. Another is adding randomness. Sometimes take a slightly worse step to escape a local trap. And a really effective technique is just restarting the whole greedy search many times from different random starting points. Keep trying until one succeeds. Surprisingly powerful. The source even says this method solved the 3 million queens problem in under a minute.
Wow, that's amazing scalability. So local search is great for huge problems where a solution is fine, not necessarily the optimal path. Okay, the source then transitions to planning. We touched on this.
Yes, planning.
Given.
Producing that sequence of actions to get from start to goal. The source introduces STRIPS, a standard language for formally describing planning problems.
STRIPS, acronym, what does it do?
Stanford Research Institute Problem Solver. It gives a precise way to describe the world in actions. It uses atoms, simple facts that are true or false. Our problem has an initial state, set of true atoms, a goal, set of atoms we want true, and actions. Each action has preconditions, atoms that must be true to do it, and effects, atoms that become true or false after doing it.
Very logical. The source uses a simple pizza example.
Yeah. Shows strips for getting pizza. Goal: be home, have pizza. Initial state: have money at home, phone works. Actions: call, go, return, order, buy. Each has preconditions. The example: need money to buy, and effects: buying has pizza true, has money false.
Clear. And then a more complex delivery robot example.
Right. Delivering a DVD and book using trucks playing between cities. Initial state: locations of everything. Goal, items at destinations. Actions.load truck, load plane, unload, drive, fly. The source details the strips for plane actions, showing the level of precision needed. It emphasizes this scales up to realistic problems.
So once we have a strips description, how do we find the plan? Search algorithms again?
Yes, two main approaches discussed. So forward search and backward search. Forward search is what we've mostly seen. Start from the initial state, apply actions step by step until a state satisfies the goal.
Standard search.
But in planning, the number of possible action sequences can be huge. Uninformed search often isn't feasible. Even the delivery robot example, maybe 17 steps minimum, with maybe 5+ options each step. That's over 517 paths. So heuristics are usually needed to guide forward search and planning, though the source doesn't detail them here.
Okay, forward search needs guidance. What about backward search?
Backward search starts from the goal and works backward. It asks, what action could have resulted in this state, or parts of the goal, and what needed to be true before that action?
So, what needed to happen right before I achieved my goal?
Exactly. States here are sets of goal atoms we still need to achieve. The initial search state is the planning goal. Actions are relevant. Strips actions whose effects match some needed goal atom. Applying an action backward means removing its positive effects from the needed set and adding its preconditions. The search goal is reached when all atoms in the current needed set are true in the original planning problem's initial state. The plan is the sequence of actions found, reversed.
The pizza example again for backward search.
Yep, figure 2 shows it. Start with Golem has pizza. Relevant actions. Return. Achieves at home. Buy. Achieves has pizza. Explore their preconditions backward, finding the sequence return, buy, go, call. Reverse it. Call, go, buy, return. That's the plan.
Seems more focused on the goal. Downsides.
A key challenge. Backward search can generate sub-goals or states that aren't actually reachable from the real initial state, like needing to be at home and at the restaurant simultaneously. Exploring these impossible states is wasteful. Characterizing reachable states is hard, but sometimes partial checks can prune the search. Also, heuristics can be adapted for backward search too.
The source then briefly mentions limitations, real-world complexities like conditional actions, randomness.
Right. Basic strips assumes deterministic, instantaneous actions. The real world has conditional effects. If X, then Y. Non-deterministic outcomes, action might fail. Actions take time, temporal planning. Actions depend on knowledge. Check email needs password knowledge. Multiple agents coordinating. These require more expressive planning formalisms beyond basic strips, which the source just touches upon.
Sounds like realistic planning gets very complex. Now games. We saw how they can be formalized as problems.
Yes, and this section focuses on a specific class. Finite, deterministic, two-player, turn-taking perfect information, zero-sum games.
Okay, break that down.
Finite, they always end. Deterministic, no randomness like dice, two players taking turns, perfect information, everyone sees everything, like chess, not poker. Zero-sum. One player's gain is exactly the other's loss. Win-loss draw. Tic-tac-toe is a perfect example. Chess, checkers also fit.
So no chance, no hidden cards, clear win or lose or draw. How do we formalize these for AI?
Initial state, board setup, whose turn. Successor function defines legal moves, resulting states. Terminality test is the game over. Utility function assigns value to end states, +1 for max win, -1 for win max loss, 0 for draw. In zero sum, 1 value is enough.
In tic-tac-toe, used as an example again?
Yep. Empty grid, X starts, actions, place XO, terminal, 3 in a row or full board, utility, +1, -1, 0.
These games can be visualized as game trees, right?
Exactly. Noders are game states, edges are moves. Leaves are terminal states with utility values. Nodes alternate between max, player trying to maximize score, and min, player trying to minimize max's score. Figure 1 shows part of the tic-tac-toe tree.
And we're looking for a strategy, a plan for every possible situation.
Right. An optimal strategy guarantees the best possible outcome against a perfect opponent.
So how do we find these optimal strategies? Enter the Minimax algorithm.
Minimax finds the optimal strategy by calculating the minimax value for each node. This value is the best outcome the current player can force in that state, assuming the opponent also plays optimally.
How do we calculate these values?
Start at the bottom, the leaves. Their minimax value is their utility, then work up. For a max node, its value is the maximum of its shoulders values. Max chooses the best outcome for them. For a min node, its value is the minimum of its children's values. Min chooses the worst outcome for max. The source gives the formal recursive definition.
And figure 2 shows this calculation on a simple tree.
Yes, step by step. Values propagate up from the leaves, determining the minimax value for each node right up to the root. The root's value tells you the game's outcome with perfect play.
And once we have these values, we know the best move.
Exactly. At a max node, choose the move leading to the child with the highest minimax value. At a min node, choose the move leading to the child with the lowest value. The example shows finding the optimal first move this way.
And it can be coded recursively. Figure 4 shows a more complex example.
Yep, same process on a bigger tree. Shows values propagating up. Root value ends up being 0, meaning perfect play leads to a draw. Max can't force a win, but can avoid a loss. The source also briefly notes extensions for multiplayer utility vectors and chance games expect to minimax.
Minimax seems solid, but sounds slow for huge games like chess. That's where alpha-beta pruning comes in.
Exactly. Game trees for chess, Go, etc. are astronomically huge. Exploring the whole tree is impossible. Alpha-beta pruning is a very clever optimization. It gets the same minimax result, but by looking at potentially far fewer nodes.
Cuts down the search.
The core idea. You can often stop exploring a branch if you've already found a better alternative elsewhere. Alpha-beta keeps track of 2 values during the search. Alpha, the best score max is already guaranteed somewhere else on the tree, and beta, the best score min is already guaranteed.
Alpha and beta bounds.
Right. If you're exploring a min node and find a move that leads to a score less than or equal to alpha, you can stop exploring min's other moves down that path. Why? Because max already has a better option, alpha, and will never let the game reach this point. You prune the rest of that branch. Similar logic applies at max nodes using beta.
The source gives the detailed recursive algorithm. Looks a bit more complex.
It is, with passing alpha and beta down. But the key is those pruning conditions. Stop exploring below a min node if its value drops to alpha. Stop exploring below a max node if its value rises to max. Initially call it with alpha infinity, beta plus infinity.
And it gives the same optimal moves as Minimax.
Guaranteed. Same result, just potentially much faster.
The source notes its effectiveness depends on move ordering.
Critically, worst case order, no pruning. Best case, always exploring best moves first. Complexity drops significantly, roughly the square root of Minimax's complexity. Still exponential, but lets you search maybe twice as deep in the same time. Heuristics are used to try and achieve good move ordering in practice. Also noted, alpha-beta doesn't work as well for more than 2 players or with expect a minimax.
Even with alpha-beta, real-time games need more tricks. Real-time decisions.
Yep, still can't search to the end in chess. So you cut the search off at some depth and use an evaluation function to estimate the goodness of the board position at that cutoff point.
An educated guess of who's winning?
Pretty much. Use exact utilities plus 110 if you hit a terminal state before the cutoff, otherwise use the evaluation function score. The quality of this function is crucial, often handcrafted by experts, but can also be learned via machine learning, like TD Gammon for backgammon.
So estimate instead of full search. Other techniques.
Selective deepening. Instead of a fixed depth, search deeper along promising lines. Singular extension search. If one move looks way better than others, follow it deeper. Deep Blue did this. Quiescent search. If the evaluation score is changing wildly, unstable position, maybe captures happening, search a bit deeper until things calm down. Deep Blue and Chinook, checkers, used this.
And using memory.
Transposition tables. Store the evaluation of board positions you've already calculated. If you reach the same position via a different move order, just look up the stored value. Saves recomputation. Also, memorization of openings, endgames. Deep Blue had huge databases of openings, master games, and pre-calculated endgames. Chinook knew all positions with 8 or fewer pieces.
Wow. Building a top game AI is a mix of smart search and massive knowledge. Okay, next section. Knowledge representation. Goal here.
Studying formal ways to represent knowledge so a computer can use it. Focus here is on logical languages, though probabilistic ones are also key in AI. It starts with refreshers on propositional and first-order logic.
Let's start with propositional logic. True-false statements, right?
Exactly. These are units of propositions, PQ, which are true or false, combined with Gaindier and Arsha, not derived. Implies AF. Literals are poor pig. B. Clauses are ORs of literals. The model assigns true-false to each proposition. Satisfaction, when a formula is true in a model. Concepts, .valid, always true. Satisfiable, true in at least one model. Logical consequence, if to an end must be true. Decidable, but checking satisfiability can be computationally hard. MP complete.
Okay, basics covered. First order logic is more powerful.
Much more expressive. Adds constants, variables, functions, mother of egg, predicates, human x inside x, y. Adds quantifiers. For all there exist, terms are constants, variables, functions applied to terms, atoms or predicates applied to terms or equality. Formulas combine atoms with connectives and quantifiers. Model needs a universe of objects, U and interpretation, mapping symbols to meanings in U. Valuation assigns variables to objects in U. Satisfaction defines truth. Key difference. First-order logic is undecidable. No general algorithm can always tell if a formula is valid.
Undecidable. Big difference. The source then glances at other logics. Description logics.
Yeah, description logics sit between propositional and first order. More expressive than propositional, but often decidable, unlike full first order. Good for defining concepts and relationships, for example, bird-animal. Used in medicine, semantic web. Temporal logics add time operators, always eventually, for reasoning about change, used in verifying software.
And fuzzy logic, knowledge-belief logic.
Fuzzy logic allows degrees of truth, 0 to 1, not just true-false. Good for vague concepts like tall, used in industry. Logics of knowledge-belief reason about what agents know or believe, including about others' knowledge. Important in AI, economics, distributed systems.
Last one, non-monotonic logics. Sounds different.
They are. Standard logic is monotonic. Adding facts never invalidates old conclusions. Non-monotonic logic allows conclusions to be retracted when new information arrives.
Like real life.
Exactly. Example, Tweety is a bird, Tweety flies. Add, Tweety is a penguin, retract Tweety flies. Handles default assumptions, incomplete info. Default logic is one type mentioned.
Seems much more realistic. Okay, after representing knowledge, automated reasoning, making use of it.
Right. How to draw conclusions. Distinguishes deductive, guaranteed conclusions, abductive, finding best explanation, inductive, generalizing from examples. This chapter focuses on deductive reasoning in propositional logic.
Okay, deductive logic. 2 main tasks.
Testing if formula A is a logical consequence of A, and generating consequences of A. Mentions truth tables, satisfiability testing, check if A is unsatisfiable. Then introduces the resolution rule.
Resolution, key method, works with clauses.
Yes, rule. If clause 1 has literal L and clause 2 has literal L, you can create a new clause by combining the rest of clause 1 and the rest of clause 2. This new clause is a logical consequence, works for testing and generating consequences, extends to first-order logic too.
To use it, formulas need to be in clausal form.
Correct. Everything is a set of clauses, or R's of literals. Source gives steps to convert any formula. Eliminate A tato, push inwards to Morgan's, distribute A over Harris. Gives an example conversion.
Then use resolution to reason.
Yep. To test satisfiability. Convert to clauses, repeatedly apply resolution. If you derive the empty clause, contradiction, it's unsatisfiable. To generate consequences, prime implicates, convert, apply resolution exhaustively, add all resolvents, then remove redundant clauses. Source gives algorithms and examples for both.
This shows how AI performs logical deduction. Okay, last big topic, introduction to learning, specifically machine learning.
Yes. ML systems learning from data experience without explicit programming for every task. Source outlines 3 types based on available info: supervised, unsupervised, reinforcement.
Briefly.
Supervised. Learn from labeled examples, input-output pairs, like learning to recognize digits from images labeled 0 to 9. Unsupervised, get only raw data, find patterns or structure, like clustering customers. Reinforcement. Agent learns by acting in an environment and getting rewards penalties. Learning chess by playing, getting reward for winning. They're complementary.
And the source focuses on the decision tree method, an example of supervised learning.
Right. Popular for classification. Build a tree structure from labeled data to predict the class of new examples. Big advantage. Relatively easy for humans to understand the rules learned, unlike maybe neural nets.
How does it work? Spam example.
Yeah, classify emails as spam, not spam, based on attributes. Sender known keywords, HTML, capitals. Tree has tests and nodes, where example is sender known. Branches for answers, yes, no. Leaves give classification, spam, not spam. To classify new email, follow path down tree based on its attributes.
But multiple trees possible from same data, how to choose the best.
2 criteria: coverage accuracy, how well it classifies training data, and simplicity, fewer nodes preferred. Simpler trees often generalize better to new data, avoid overfitting. Overfitting is learning the training data noise, performing badly on unseen examples.
Makes sense. And the source gives the ID3 algorithm to build trees.
Simplified version, yes. Recursive algorithm. At each step, pick the attribute that best splits the data, the one providing the most information gain. Repeat until nodes are pure, all examples same class, or no attributes left.
Information gain, based on entropy.
Exactly. Entropy measures data impurity, mix of classes. Information gain is the reduction in entropy achieved by splitting on an attribute. ID3 picks the attribute giving the biggest gain. Source walkthrough spam example. Calculate initial entropy, calculate gain for each attribute, auteur, mock clays, HTML, majuscule. Pick a tour highest gain as root. Recurse on subsets. Builds the tree in figure 1. Mentions extensions for numbers, missing values, pruning, ensembles, multiple trees, to improve performance, though maybe reducing interpretability.
Wow, we have really covered a massive amount of ground on AI today. A true deep dive.
We certainly have, from wrestling with the definition and tracing its history to mapping out all the subfields.
Exploring how AI searches for solutions, makes plans, plays games like chess.
How it represents knowledge with logic, reasons automatically, and even starts to learn with things like decision trees. It's a huge landscape.
There were definitely some aha moments for me. That space shuttle flying itself, incredible. And the savings from that Army logistics AI, just staggering.
Yeah, and Deep Blue's massive chess knowledge base is mind-boggling too.
Yeah.
Even that Tweety example for non-monotonic reasoning, it really shows AI trying to tackle messy, common sense stuff.
These examples really drive home the breadth and impact of AI, don't they? It's built on some deep theory, but has very real applications.
Absolutely.
So for you, the learner, we really hope this deep dive has given you a solid foundation in the core concepts of AI. There's clearly so much more to explore in every single area we touched on.
Oh, for sure. Each section could be its own deep dive series.
But hopefully now you have a framework, a map, to build upon as you continue your journey learning about this incredibly fast-moving field.
And maybe, as we wrap up, something to think about. As AI keeps advancing, getting woven more tightly into our lives, how might our own understanding of intelligence itself, both artificial and human, keep shifting and evolving? It's a fascinating question, and one that will definitely shape the future of AI.